Welcome to the Introduction to Dynamic Behavior and Feedback Structures lesson. Nowadays, more than ever, we're surrounded with data charts about all sorts of phenomena. As you can see from the cartoon, an employee is buried in piles of charts, maybe not as papers, maybe on his phone or on his computer, and his boss is demanding him to move ahead with his task and come up with practical insights. But in order to know what to do about all those data charts, we need to know why they behave the way they do. This brings us to the topic of our unit today about dynamic behavior and feedback structures. The learning goals from this unit are: understand dynamic behavior and its link to feedback structures, and recognize feedback loops we face in life. By the end of this unit, you will be able to name different types of dynamic behavior, identify the elements of feedback loops, explain the difference between feedback loop types, and provide examples of positive and negative feedback loops. We will have 2 one-minute practice exercises through this unit, so let's begin. So what is a dynamic behavior? It describes a phenomenon that changes over time. You may have seen such data charts showing the number of COVID-19 cases growth, decline, and in some cases they rise again over a period of time. You may also have heard or read terms like exponential growth, reaching the peak, declining cases, flattening the curve, or maybe recently a second wave. Those reflect dynamic behavior in the form of growth, decline, or oscillation. So I'd like to start with a story to explain how a dynamic behavior can be generated. The story is about the COVID-19 pandemic. As you can see on screen, let's assume we have an infected case that you can see on the chart below as a single case. Over time, you may have more cases coming, say, into a country, which increases the number of infected cases from 1 to 10. The pipe shows the flow of those cases into the box of infectious population. We call the pipe a flow and the box a stock. Each of those infected live in a community, which makes the community susceptible to infection. Nothing will happen if they stay in isolation, though. Therefore, you see the number on the chart remains constant at a value of 10. Once they start mixing with others, as you can see through the pipe connection from the susceptible population stock on the left to the infectious population on the right, something will happen. What is it? You're right. Infection will start. More infectious population infect more susceptible population, which results in more infectious population, which changes the curve on the chart to grow rapidly. We call this exponential growth. It is fueled by a reinforcing loop between the infectious population stock and the infection rate. It is labeled with R for reinforcing. But will the number of infectious population continue to grow, or there will be a limit? Yes, you're right, there will be a limit. With more people infected, there are less people to be infected, which limits the growth of infection. We call the loop between the susceptible population stock and the infection rate a balancing loop labeled with the letter B. You can see the resulting behavior in the chart below. The blue curve reaches a maximum and then equilibrium at around 10K, where the red dotted line declines to 0, reflecting a decline in the susceptible population. Now the question comes, will the stock of infectious people remain at that level? Actually, no. The stock of infectious people will decline, as you can see on the blue curve, where people either recover or die. It is shown through a connection between the stock of infectious population and the removed population. The chart shows a decline in the number of population as the declining blue curve, and a growth in the removed population as the growing magenta curve. In summary, this was a quick description of an epidemic dynamic behavior. It is generated from the action of three feedback loops. A reinforcing feedback loop increases the infection, as you can see in the blue curve. A balancing loop limits the growth of the infection to a certain peak there. And another balancing loop which decreases the infectious population to become removed. So we can say that behavior or the dynamic behavior results from a structure. This has been a quick story describing the popular susceptible, infected, removed SIR model. The diagram shows more model details. On the side there is a link to the simulation model that you can experiment with online. And on the bottom right, you can generate such profiles of infectious population, among which is what we call flattening the curve. This goes beyond the scope of this introduction and can be explained in other lessons. Two key systems thinking concepts came as we went through the story: stocks and flows and feedback loops. So let's start with the stocks and flows. As you recall, the connected pipes and box in the story, the pipe is a flow and the box is a stock. The closest analogy is the bathtub analogy. The water that flows into the bathtub is called an inflow, and the water that drains from the bathtub is called an outflow. The flow is how much water is flowing over a unit of time. In this case, it could be cubic foot per minute or cubic meter per minute, depending on the units you use. It reflects how fast or slow the water is added or removed from the bathtub. The level of the water in the bathtub is a stock. A stock represents accumulation. You can measure the volume of water in liters or cubic foot or cubic meters. And on the side, we see that if the inflow equals the outflow, then the level of the stock doesn't change. If the inflow is greater than the outflow, then the level of water will increase. That's a growth. If the inflow is less than the outflow, then the level of water will decrease, and that's a decline. The integral equation that you see on the slide provides a mathematical explanation of the stock and flows structures, but we will not go over it here. Examples of stocks and flows can be tangible or intangible. For example, water in the ocean is a stock. Evaporation is a flow. Water in clouds is a stock. Precipitation is a flow. Body weight is a stock. Gaining weight is a flow, and losing weight is a flow as well. Anger is a stock, although hard to quantify. Building anger is a flow, and so does venting through different means people do to vent their anger. Now we will pause for a practice exercise. That will take us 1 minute. Next, let's talk about feedback loops. There are two types of feedback loops: positive or reinforcing feedback loops, where an action creates a result which influences more of the same action, thus resulting in a growth or a decline. That's, in summary, says an increase in one variable leads to an increase in the linked variable, or vice versa. As you can see, the positive signs on the arrow tips indicating that increase in A results in increase in B and B increases A. Negative feedback loops or balancing feedback loops, however, they represent actions that attempt to achieve a goal or close a gap from the current state and the objective. So this means they reach a limit. An increase in one variable leads to a decrease in the linked variable and vice versa, and that's why you see the negative sign here. They're denoted with the letter B. Examples of feedback loops. As we have more fish, we have more birth or recruitment, and as we have more recruitment, we have more fish. Yes, that's a positive feedback loop, and the resulting behavior is growth. More fish, more birth. The other kind is with more death, we have less fish, and if less fish, we have less death. And this is a negative feedback loop that results in a decline. If we combine both recruitment, death, and fish, then that's a combined feedback loop. What is the resulting behavior? It depends. If we have more recruitment than death, then the population of fish grows. If they are equal, then we have equilibrium. And if we have more death than recruitment, then they decline. Now we reached to the second practice exercise. I'd like you to pause for a minute, take the practice exercise, and we'll come back to conclude. This brings us to the end of our lesson today about the dynamic behavior and feedback structures. The learning goals from this unit were to understand dynamic behavior and its link to feedback structure, and recognize feedback loops we face in life. By now, you are able to name different types of dynamic behavior, identify the elements of feedback loops, explain the difference between feedback loop types, and provide examples of positive and negative feedback loops.